Next, equilibrium. Now imagine you are digging a hole, and as you are digging that hole, your friend is refilling it. If you are digging the hole faster than your friend, then the hole gets larger. If your friend is filling the hole faster than you, the hole gets smaller. But if the two of you are working at the same speed, then there would be no change in the size of the hole. Note that it is not that you have stopped working. No, it is just that you are working at the same speed. The same concept can be applied to a reversible reaction. If the rate of the forward reaction, that is reactants to products, is the same as the rate of the reverse reaction, that is products to reactants, the reaction is said to be at equilibrium. This is called a dynamic equilibrium because both processes are occurring simultaneously, even though there are no observable changes. For a chemical system, such as a reaction or a phase change, to be at equilibrium, it must meet two important criteria. First, it must be a reversible process, and secondly, it must be taking place in a closed system. A closed system is one in which there is no exchange of matter, only exchange of energy. An example of a reaction at equilibrium is the reaction between hydrogen and iodine in a closed container to produce hydrogen iodide. At the start of the reaction, there is a high concentration of hydrogen and iodine, and the concentration decreases as the hydrogen iodide is formed. The concentration of hydrogen iodide increases as the forward reaction proceeds. As the hydrogen iodide is formed, the reverse reaction is now able to occur. Over time, the concentration of hydrogen, iodine and hydrogen iodide remain constant. Why is that? The reaction of hydrogen and iodine to produce hydrogen iodide is occurring at the same rate as the decomposition of hydrogen iodide to hydrogen and iodine. So there are no observable changes, although both forward and reverse reactions are occurring. The reactions have not stopped, but rather have reached a dynamic equilibrium. What would happen if the lid of the gas jar is opened? If the lid was removed, the system is no longer at equilibrium, as the reactants and the products are able to escape out of the system. Liquid bromine equilibrates to form gaseous bromine at room temperature. Remember, this is not a reaction, but a phase change. Phase changes can also reach equilibrium under the right conditions. As liquid bromine evaporates, gaseous bromine condenses. Since these two processes are occurring simultaneously at the same rate, there is no observable change. The system is in fact in dynamic equilibrium. So a system is said to be in dynamic equilibrium when the rate of the forward reaction is equal to the rate of the reverse reaction. There are no observable changes, even though both directions of the reaction are occurring. Now let's return to you digging a hole and a friend refilling it at the same rate. No observable change in the size of the hole. The system is at equilibrium. But if you start digging faster than your friend, then the hole gets larger. In order to maintain a constant size of the hole, your friend must work harder to fill it faster. Following on the same idea, when a chemical system at equilibrium is stressed, the system works to restore the equilibrium. This is Le Chatelier's principle. When a change in condition is applied to a system in equilibrium, the system moves so as to oppose the change. The stresses include change in concentration of either the reactants or the products, change to pressure in case of gases, and changes in temperature. Let us examine a hypothetical reversible reaction at equilibrium. where reactant A reacts with reactant B to form product C and D. If we add more A and B, the system becomes stressed and is no longer at equilibrium. To counteract the stress, the system forms more C and D in order to remove the excess A and B. The equilibrium therefore shifts to the right. If we added more C and D, the system becomes stressed and is no longer at equilibrium. So to counteract the stress, the system forms more A and B. Therefore, the equilibrium shifts to the left. What if we removed C and D as they are being produced, or if the concentration of C and D is decreased? The system is now stressed and is no longer at equilibrium. To counteract the stress, more C and D are produced so that the equilibrium shifts to the right. When the concentration increases on one side, equilibrium shifts to the opposite side of the reaction. When the concentration decreases on one side, equilibrium shifts to that side of the reaction. Next, changes in pressure. Now, this stress to a system at equilibrium is only applicable to gaseous systems. Consider a hypothetical reaction where 1 mole of A reacts with 2 moles of B to form product C and product D. An increase in pressure means there is a decrease in volume, so there is less space. Equilibrium will shift to the side of the reaction with fewer moles. In our example, an increase in pressure will cause the equilibrium to shift to the right since there are few moles, 2 moles compared to 3 moles on the left. A decrease in pressure means there is an increase in volume, so there is more space. Equilibrium shifts to the side with more moles, so in our case, equilibrium will shift to the left. And so an increase in pressure favors the side with fewer moles. A decrease in pressure favors the side with more moles. If the number of moles is equal on both sides of the reaction, then changes in pressure will have no effect on the equilibrium. Next is change in temperature. Now, to consider what happens to a system at equilibrium when temperature is changed, we must first consider the energetics of the reaction in question. If the forward reaction is exothermic, then the reverse reaction must be endothermic. Let us examine a hypothetical reaction where reactant A reacts with reactant B to produce product C and D with the enthalpy change of -75 kilojoules. This means that when the forward reaction occurs, 75 kilojoules of energy is released, and 75 kilojoules of energy is absorbed when the reverse reaction occurs. So an increase in temperature will mean that the endothermic reaction will be favored to remove the excess heat and therefore counteracting the imposed stress. A decrease in temperature will cause the system to produce more energy. Therefore, the exothermic reaction will be favored. The conversion of nitrogen 4 oxide to dinitrogen tetraoxide is an exothermic reaction. Nitrogen 4 oxide is a brown gas, whereas dinitrogen tetraoxide is a colorless gas. What observations will be made if the temperature is decreased or when the temperature is increased? A decrease in temperature favors the exothermic reaction, so more dinitrogen tetraoxide is produced. Since it's a colorless gas, the mixture appears pale yellow. An increase in temperature favors the endothermic reaction, so more nitrogen 4 oxide is produced. The mixture therefore appears darker brown. In conclusion, When the temperature of a system at equilibrium is increased, the endothermic reaction is favored. When the temperature is decreased, the exothermic reaction is favored. Addition of a catalyst does not affect the position of equilibrium, as it increases the rate of both forward and reverse reactions. So it only quickens the attainment of equilibrium. Let's go back to digging and refilling a hole. Imagine if you were both given bigger shovels. Although the amount of soil handled is larger with each stroke, the size of the hole remains constant. So adding a catalyst has no effect on equilibrium.